Welcome everyone. So today we are very happy to have Professor Inti Sodemann talking about non-equilibrium quantum liquids of periodically driven fermions. So welcome.
Thank you very much for the invitation. It's a real pleasure to be here. It's my first time at the University of Chicago. So thanks a lot. So today I am going to tell you about some recent investigations we have been doing on trying to understand the non-equilibrium steady states of fermion fluids when they are being periodically driven, okay? When they are being shaken by some periodic drive that keeps them away from equilibrium. Let me introduce first my collaborators. So all the hard work, all the heavy lifting in this project, these projects has been done by these two talented young scientists, Li Kun, who is a postdoc at the Institute of Theoretical Physics in Leipzig, where I am, and Oles, who is a postdoc working with my collaborator, Justin Song, in Singapore. Just a little bit of advertising about where I am. So I'm at the Institute of Theoretical Physics at the University of Leipzig. It's a place with very rich history. So it's the place where Heisenberg used to be a professor, and where he, trained some of his PhD students were, the people who laid out the foundations of, various aspects of solid state physics. So people like Bloch, Peierls, were his students in Leipzig. He spent sort of the golden years of his career there, when he won the Nobel Prize and so on. And so we're not very far from Berlin and Dresden, about an hour by train in Germany. So if you're ever in Germany, please let me know. It would be great to have you visit us. So the talk is structured into three parts. I will first present some kind of overview, and essentially to set the stage of how I want to think about this problem of periodically driven fermions. We will revisit some general points. And then there will be essentially two parts, okay? In a sense, one of the main messages I want to convey is that the answer for the steady states of systems that are out of equilibrium depends much more on the details of the path of how the system is reacting, how it's. So we're going to find two completely different answers when we have a kind of grand-canonical setting in which the fermions are coupled to a bath with which they are only exchanging energy. The steady state is going to look completely different. Sorry, in this case, when they are exchanging energy and particles with the bath, so a grand-canonical setting, we're going to have a very different answer to the case in which they are coupled to a bath with which they are only exchanging energy. Okay, the steady states are going to look very differently. And that's maybe one of the key things about non-equilibrium, as I will try to show you, that these details of the bath really matter much more than in equilibrium. Okay. And so let's start, by imagining that you have some many-body system that has a Hamiltonian that depends on some parameter. Let's call it y, okay? That could possibly be time dependent. If this parameter is time independent, let's say, imagine it's just the height, for example, of the piston that is driving the gas. If this parameter is time independent, and you prepare the gas into initial states that have the same initial energy, but they might be very different states. As we know, after you wait a long time, they will approach some state that can be described by the same, equilibrium density matrix as, we know from, textbooks of statistical physics. So the system will essentially lose all memory of initial conditions. It will thermalize into some unique state if we leave this parameter of the Hamiltonian constant, okay? But now imagine that we start changing this parameter, the height of this piston, as a function of time. So for most of the talk, I will restrict to the case in which is this variation of the parameter of the Hamiltonian is periodic in time with some period t. But generally, we could also imagine that this is just some given function of time. So you're given the Hamiltonian and you're given this parameter. And so, how should we write down the density matrix that describes the steady states of this system after a long time? So this is a very difficult problem in general. We don't have general principles as we have in equilibrium. Entropy maximization essentially tells us what is the ensemble we can use here. But out of equilibrium, we don't know, how to even write the ensemble. Not to mention even how to start computing once we know the ensemble. It's already very complicated in equilibrium. Out of equilibrium, we don't even know in general how to start computing because we don't know the ensemble. And so, this is just to say very briefly, this is the essence of why it's hard, but it's also, in a sense, what makes it interesting that it's a very open problem, okay, to determine what are the kind of rules that we should use, or the descriptions we should use to describe the steady states of driven systems. And this talk is about, I will try to show you that the answers can be quite interesting by considering this problem of how fermions, what is the steady state of periodically driven fermions? What is the nature of the kind of blockade or periodically driven fermi-liquid, okay? So let's start with some general considerations. So I want to motivate why we need to consider that the system is open, okay? So let's just go back to the second law of thermodynamics. So imagine you have some parameters that you are changing periodically. So, it might be the height of the piston, but you also might have magnetic field acting on the gas. And imagine that these parameters are, traced in some loop in parameter space. So if you change these parameters at any finite rate, when the parameters return to the initial point, the gas will not go back to the initial state. If this is done at any finite rate, the gas, by the second law of thermodynamics, will become, when you come back, will have higher energy. That's what the second law tells us, okay? So the work that you do in a closed cycle, if you perform this at any finite rate, generically for a thermodynamically well-behaved system, will lead to heating. So the energy will always be larger than the initial energy, typically. And so that is what gives rise to the so-called thermal death in closed blockade systems. So if you have a system that is closed and is essentially a thermodynamically well-behaved system, and you start changing the parameters of the Hamiltonian periodically, every time you complete the cycle, the system will be slightly hotter. And if the spectrum is not bounded, this means that the system will just keep heating indefinitely to infinite temperature. So there is no, if the system is thermodynamically well-behaved and it's closed, by the second law of thermodynamics, we do not expect to have generically kind of interesting steady states. And that's the reason why it's important, or to make the question kind of not that trivial, it's important that we consider a system coupled to a bath. So we're going to imagine this bath is actually, as we will see, an explicit physical system that is just much larger than the system. So it's taken to the thermodynamic limit in a sense faster than the system, we will see. But so we will imagine that there is this bath, and then we will be changing the parameters of the Hamiltonian in some cycle periodically at finite rate. But after a while, the system will reach a steady state in which the amount of work, the amount of energy that you put into the system by changing parameters leaks equally into the bath. And so the energy density does not grow. So the system reaches a steady state in which you change the parameters periodically, and the energy itself also becomes periodic in time. So we will be interested in trying to understand what are the ensembles of these late time steady states of quantum systems coupled to baths that are periodically driven.
If you didn't have precisely periodic driving, you came back very close or some non-closed loop in parameter space, is there any reason to think there would be a steady state at the end, or?
I would say, yeah, that's a very good question. So, I would say generically after you wait a long time, the systems will tend to approach a kind of limit cycle. They will, if they are thermodynamically well behaved, they should erase memory of initial conditions and approach some kind of unique limit cycle. Yeah, so this in a sense connects to what you were asking. So in a sense, there is a sense of thermalization, or you could call it synchronization, in that, if initially my gas had two very initial different states, maybe the gas kind of piled up in this corner, maybe some other state in which it's more spread in this other corner, two very initial states. After you drive the parameters of the Hamiltonian for a long time, both states will, the system will evolve into a kind of limit cycle, which is actually unique. Generically, for a well-behaved thermodynamic system, it will be a unique limit cycle. So there's a unique kind of steady state ensemble, which is just very hard to compute and hard to know what it is, but there will be a unique state. So there's some sense of thermalization or of approach to some, or synchronization, you could call it. The system will start shaking itself with a period that is identical to the period of the drive and will erase all memory of details of the initial conditions. And so that's kind of what we're after. What is this steady state in the case of fermions when they are, periodically driven? And so here is maybe, this slide is really one of the main messages of the talk. So I want to kind of give the punchline before I show you I will illustrate this with the specific examples, but this is kind of one of the important conclusions or messages, okay? There exists no zero law of thermodynamics in this setting of, periodically driven open systems. So what do I mean by that? So in equilibrium, if you have two baths and you couple them, let's call this coupling gamma, some weak coupling, two baths, so that they reach equilibrium with each other, okay? And then imagine I have, these are two baths, so now I have my system of interest. So if I bring it in contact with the first bath, with some coupling gamma 1, weak coupling, versus I bring it in contact with bath number 2, the system will always approach the same, will always approach the same equilibrium state, regardless of the details of the bath. So just picture maybe your system is like fermions, and here you're coupling it to bosons, and here you're coupling to some spin system, okay? As long as these systems are very large, and this coupling is very weak, there's a remarkable universality in equilibrium, which is basically encoded in the zero law of thermodynamics, that there is a transitivity of thermal equilibrium. So if I equilibrate it with this guy or that guy, I'm gonna get the same as long as those guys are in equilibrium with each other, right? That, I will show you, does not hold out of equilibrium. So even if you have two baths that, they are not driven, they are in equilibrium, and you are, driving this height of the piston at some, in a periodic way, for example, the steady state that the system reaches when you couple it to a bath, let's say, of spins, versus when you couple it to a bath of bosons, is going to be actually a completely different steady state. So the steady state, in the end, it's going to be unique, and the system is going to erase memory of initial conditions, and it's going to flow to that unique steady state, but is going to be something that is not going to be just a functional of the Hamiltonian of the system and some unique parameter like temperature. It's going to know also what is the nature of the bath, okay? So to summarize, the bath matters out of equilibrium. Two baths that will give you the same steady state in equilibrium will generically lead to different steady states when you're driving. The nature of the bath matters. And so here is kind of the summary of the concrete sort of versions of this general statement I just made. Okay, so we're gonna investigate two examples or two settings in which we're going to see this very clearly. One is going to be the one that I call a grand-canonical setting. So in this case, we're going to take a Fermi gas. We're going to be driving it periodically, and it's going to be coupled to a Fermi bath. So the Fermi gas can exchange energy with this bath, but it can also exchange particles. So the particles can kind of tunnel in and out of the system. And so in equilibrium, the system will have, the occupation of states will be given by the Fermi-Dirac distribution. But what I will show you is that in the non-equilibrium setting, when this is being driven periodically with some frequency omega, the occupation of states of the Fermi gas will actually have a kind of staircase shape with several jumps, like several Fermi surfaces actually, in this setting. Okay, so we call this state a Floquet fermi-liquid because it actually behaves as if you had several Fermi surfaces with different kind of effective residues, effective quasi-particle residues, but essentially behaves like a Fermi liquid. Okay, that's the steady state with this kind of bath. But when you change the bath, so when I couple my Fermi gas, the same system as before, and the same driving, I'm keeping the driving and the system the same, just changing the bath. Now a boson bath in which the system can only exchange energy, there is no particle tunneling. What I will show you is that there is a very non-trivial steady state. So instead of occupying states according to Fermi-Dirac, the system has an occupation that retains some non-analyticities that are like kinks in the occupation of the states. And so it behaves as a kind of non-Fermi liquid. So the states are occupied with some function that has some cusp or kinks that behave effectively for some phenomena, as I will show you, as the Fermi surfaces of a non-Fermi liquid. And the even more amazing thing we found is that in the case of the Fermi bath, when the bath has finite temperature, all of these steps smear out just like in a Fermi liquid, just like in a free fermion setting. But in this setting, the kinks actually remain sharp even when the bath is at finite temperature. And we call this, the system remains ultra critical. I will explain what that means. But it's essentially that these kinks remain sharp even at finite temperature. So yeah, so let's kind of very briefly review the basics of Floquet theory. So you have Schrodinger's equation in equilibrium with eigenstates and eigenenergies. And when you have a Hamiltonian that is now changing in time with some period t and frequency omega, then we can define Floquet wave functions and Floquet energies, where the Floquet wave function is kind of the periodic part of the wave function, can be expanded into Floquet harmonics, and there will be a Floquet energy. Okay. One important point is that the number of linear independent solutions of the Schrodinger equation does not change just because the Hamiltonian is time dependent. So one can always fix a gauge so that the number of states, the number of Floquet states, is the same as the number of states that you had in equilibrium. And in the case of a Bloch band, basically, if I have imagine I have a crystal and there is a Bloch band in equilibrium. Let's imagine for simplicity, that there are no other bands nearby. This band is very isolated, so I can maybe model the system as a tight binding model with a single state per unit cell. And now when I drive the system with light, there is going to be a kind of deformed version of that Bloch band. It's going to be the Floquet Bloch band. Generally, it could be very complicated, much more complicated. But the point maybe to kind of emphasize is that the number of states is going to be the same. So if I had originally a system with a single Bloch band, I'm going to have a system with a single Floquet Bloch band. And so one state per moment. And the question, in a sense, just for simplicity, just imagine it's a single band kind of problem, is how should we fill these states, right? So as I told you, in equilibrium, we fill them with Fermi-Dirac. How should we fill this Floquet band? Is the Fermi surface still sharp? Is it well defined? And what is the occupation, right? So that's the question. Yeah.
So here, I guess implicitly here, we're working like a single particle picture.
Yeah. So I'm gonna imagine that the system is non-interacting particles. The system alone, when it's decoupled from the bath, is free fermions. Yeah. And so answering this question of how Floquet bands should be filled is, a very kind of timely question, and it's very important for various proposals. So, there has been, for example, very interesting proposals pointing out that if you just shine, circularly polarized light on graphene, then you get a Floquet spectrum in which there is a gap opening in graphene, and the Floquet bands would have a finite Chern number. So in this sense, you could get a kind of Chern insulator just essentially by shining circularly polarized light in graphene. But whether you will have properties like the ones you have in equilibrium, like quantized Hall conductivity and so on, crucially depends on how you should fill these bands, right? And so this has led to experiments in which people have tried to see, for example, this light-induced Hall effect in graphene, and the answer is essentially that the conductance or the conductivity is not quantized, and so it's precisely not quantized because the filling of these bands is not just Fermi-Dirac. So understanding how much a system will behave as in equilibrium, or how to engineer these systems crucially depends on answering this type of question. How should you fill Floquet bands? Are there any experimentalists in the audience by any chance? No. So I want to kind of also make a point. Maybe some experimentalist sees the recording or something. There have been many beautiful experiments on trying to realize Floquet states in various platforms, but I want to say that so far there is really no single experiment that has truly realized a Floquet steady state for occupation of Floquet bands. Most of the experiments use ultra-fast optical techniques, and essentially I would say they properly realize the Floquet Hamiltonian, but the durations of the pulses that they use is typically too short compared to relaxation time. So I believe there is no experiment that has truly realized a Floquet steady state so far. So I just want to kind of emphasize that there is really still a very open experimental challenge, right? To really realize this non-trivial true Floquet steady states. And the issues is that when in these ultra-fast experiments, they typically use mid-infrared lasers. And so the intensity that you need to achieve in order to reach the Floquet regime are very large, or they are huge. And so that's why they have to use these very short pulses, right? So, but these experiments are very far from reaching real steady states. They are essentially kind of just doing a bang, very quick snapshot of the Floquet Hamiltonian, but in a very highly excited state, still very far from reaching steady state. So, but there is a lot of opportunity in experiments.
Do these experiments have a bath? What's the bath for that?
Yeah, it's
the rest of
very complicated, depends on details, right? You might have, graphene maybe sitting on a substrate, the substrate will serve as a bath, but it might be, in this one, it's a surface of a 3D TI, so the bulk of the 3D TI is the bath.
But it's gapped. Or...
But you have phonons, you have lots of
right?
so right. So, but maybe let me just mention briefly that maybe some place in which some true Floquet steady states have been reached is on some earlier studies of two-dimensional electron gases driven by microwaves. So if you really want to reach Floquet steady states, if there's any experimentalists eventually seeing the talk, it's better to use very low frequencies and have ultra clean materials. There have been some studies in gallium arsenide, but for example, in graphene, I think this is still kind of open, like, reaching like microwave frequencies and having very clean materials is very fertile ground, I believe, for experimental, realization of these things. It has this question of how to fill Floquet bands also has implications, but for many other questions. You know, for example, the question of whether when you shine light into a metal with some frequency such that the light is at the optical gap of the metal, so away from the Drude peak, but also away from interband transitions. There was a long-standing kind of controversy in optoelectronics, which is, you know, in an ideal clean metal, if you're shining light inside the gap, will it have rectified current? And there is some old paper that said no, but actually they made a mistake. They filled the bands according to the Fermi-Dirac distribution. And I think now we have shown that there is an issue that when you actually correctly fill the Floquet bands with these more non-trivial steady states, there is actually finite rectified current. So this is another kind of this question of how to fill Floquet bands. I'm just kind of trying to give a sense that it has implications for very different discussions, like in optoelectronics and so on. Okay, but let's get more concrete. So the first set in this grand-canonical setting is actually the simplest, because here we just have a system of fermions. Let's just for simplicity imagine you have some kind of tight binding model, and you know your system of interest are like these blue sides, and they're just coupled to a larger tight binding model that is going to be the bath. So there is just hoppings, you know, between various sides. But the point is the system as a whole is just a non-interacting system. It's a large tight binding model. And so because of that, you can integrate out this bath, these extra sides, exactly. Without approximations, you can solve the problem of what is a steady state exactly. Yeah, so you can, you know, derive a kind of Schrodinger equation for the single particle, the amplitude in the system. It will have three terms, so like the system part, that is the part that depends on time and is being driven. Just picture like these hoppings might be time dependent. There's going to be some term that is going to contain decay and memory, and some part that knows about the initial condition of the bath at some distant past, in which, you know, you prepare it in thermal equilibrium. But, you know, the kind of one important point is that here the problem can be solved exactly. So all we have to do is to kind of declare that the bath is prepared in a Fermi-Dirac distribution at -infinity at a distant past, solve this equation for the system wave function, and then, you know, make an ensemble average to whatever we declare the bath is placed at, the states are placed at -infinity, okay? Sort of like, you know, prepare the system all in the bath sides at -infinity with some Fermi-Dirac, and then evolve this forward in time, and you will get the late time steady state. This can be done with various methods. You know, people do it often with Keldysh, but the point is that you can solve the problem exactly, okay? And so to make it a bit simpler, it's useful to imagine, you know, you take this bath to be just a collection of energy levels, and you imagine that they have a density of states that is very broad compared to the system bandwidth. In that limit, all this memory. So you see this kind of effective Schrodinger equation has memory, so it knows about the past. But in this limit in which the bath has a very broad spectrum, the system essentially loses memory. The non-locality in time disappears, so the problem can be solved a little bit more easily in that limit. But you can compute exactly the steady state in that limit, and take the limit in which this coupling of the system sides to the bath goes to zero. So like this tunneling between the bath sides and the system sides is going to zero, while keeping the Hamiltonian of the system driven in time. So here I'm imagining that I'm driving this tight binding with some, you know, spatially uniform electric field and just some time-dependent vector potential. So usual parallel substitution. And so one can compute then the late time steady state, and in the limit of with coupling to the bath, one finds this formula, okay? So let me kind of explain it. So this is here we are imagining the system has a single side per unit cell, just for simplicity. So all the states can be labeled by crystal momentum. So this tells you how many fermions you have at a given crystal momentum. Okay, so it's a sum of different Fermi-Dirac distributions. F0 here is the usual Fermi-Dirac distribution. epsilon bar is the Floquet energy, and this omega is the frequency of the drive. These phi squares are the Floquet wave functions. So the Floquet harmonics, you decompose the Floquet wave function at every wave vector into harmonics, and each harmonic has an amplitude. So these amplitudes serve as a kind of weight. You add up different Fermi-Dirac distributions shifted by multiples of the driving frequency from the chemical potential of the bath, but with different weights. These weights add up to 1. So the total jump is 1, but each of the little jumps now has a fraction of what you would have in equilibrium. So in equilibrium, you will have all of these harmonics will go to 0, and you won't only have one principal harmonic that is, the wave function becomes time independent, so it's just the L equals 0 harmonic. And so in the limit in which you go to a time independent problem, all of these extra jumps go to 0, and you recover the usual Fermi-Dirac distribution. But as the amplitude of the driving grows, then the idea is that you're going to start getting an increasing size of these additional kind of jumps, okay? So the occupation is really, and you can think of this in momentum space. So this is really the occupation of states in momentum. You're going to get additional kind of Fermi surfaces, additional jumps that grow as the amplitude of the drive grows, okay? And so, one interesting point is the following. This occupation, yeah.
Sir, in your solution in the last slide, where is the data about the bath coming into?
Yeah, so the bath in this limit in which the density of states of the bath becomes infinitely broad, there is only one coupling constant, which is the density of states of the bath and the amplitude of tunneling into the bath. So this gamma.
But aren't you sending gamma to 0 there?
Exactly. So you see, there is a formula here that has finite gamma. So we have a solution like a finite coupling to the bath. And this is the limit in which the coupling to the bath goes to 0. If you were in equilibrium, if the Hamiltonian was time independent for the system, and you would have finite gamma, then the states would have a finite lifetime. So that already will give you a kind of broadening of the Fermi-Dirac in equilibrium. So in the limit of gamma going to 0, you recover the usual equilibrium Fermi-Dirac. So that's kind of the usual limit in which the bath becomes ideal, that the coupling of system to bath is weak, so the bath behaves like an ideal bath in equilibrium, but now this is the behavior that you have out of equilibrium. Okay, so even when the coupling to the bath is weak, in a sense, the bath, by its infinitesimal coupling to the system, selects a specific occupation of states. So the occupation of states is independent of, it doesn't go back to equilibrium, even though the coupling to the bath is going to 0, but the bath selects a specific occupation of states. Okay. And so there is one interesting aspect of this occupation, which is, this occupation is not a function of the Floquet energy alone, right? In equilibrium, how you occupy states only depends on what is the energy of the states. You could have two states with completely different wave functions, right? Or completely different block wave functions. As long as they have the same energy, the fermions always occupy them equally. The occupation only cares about energy, not about wave functions in equilibrium. In this setting, the occupation is not a function only of the Floquet energy. So you could have two states that have exactly the same Floquet energy, but they have different Floquet wave functions, and they will have different occupation out of equilibrium. And this is closely related to why you can have rectified current out of equilibrium. So the current basically is, occupation times quasi-particle velocity. You can show that in the Floquet setting, the current can also be written as occupation, this occupation times a kind of quasi-particle velocity associated with the Floquet energy dispersion. So you have the same kind of relation that you have in equilibrium, but there is a key difference that this F, this occupation, is not a function of the Floquet energy alone. If F was a function of the Floquet energy alone, this would be a total derivative. So when you integrate over the Brillouin zone, you would get 0 current. That's why in equilibrium you have no current. No matter which symmetries the band structure has, by equilibrium you never have current because the occupation only depends on energy. Here, you can have, let's say, more occupation of the right mover. So to say, than the left mover, even if they have the same kind of Floquet energy. And so as a result, you can have current. And so in this steady state, the electrons can be kind of, be moving in one particular direction because the occupation is not a function of the Floquet energy. And that was the issue of these earlier experiments these earlier papers that had said that it was forbidden to have rectification in the ideal limit of metals. They assumed that the occupation was a function of the Floquet energy, but it's not. In general, you will have a finite rectified current. And so, these extra Fermi surfaces are real, right? So one way to see this is you can consider now the response to small magnetic field. So imagine you add a magnetic field to this system. You can solve for the Floquet spectrum and you can compute, the oscillations of observables in response to magnetic field. Usually, for a system with a single Fermi surface, then you will have oscillations that, oscillate like, the Fermi surface area divided by magnetic field, or, for parabolic fermions, it would be chemical potential divided by cyclotron energy. So that's this fast oscillation is the usual quantum oscillation. Now, because we have extra Fermi surfaces created by these extra steps of the Fermi-Dirac, there appear extra kind of oscillations. As you see, this amplitude, the envelope of the quantum oscillations is also beating here with some oscillation. And that oscillation is given by the slow oscillation is the difference of areas of the different copies of the Fermi surface, of the Floquet Fermi surface. So the point is, if you put a magnetic field and you shine light into a metal, you will see extra oscillations, extra quantum oscillations, because there are really real new Fermi surfaces that are arising because of the Floquet driving. So that was the canonical setting, the grand-canonical setting, when you are having a fermion gas coupled to a larger fermion system. So now let me describe what happens when I have my Fermi gas and I couple it to a boson bath. This problem is much more complicated. Yeah.
Sorry, can you, I didn't understand where the dependence on the block wave function entered in the previous thing. In this L,
Here,
it's this L.
Yeah, this phi L square is the Floquet wave function. So these are the amplitudes of the Floquet harmonics. So the Schrodinger, the full wave function is psi of t. You decompose it into harmonics, and the amplitudes of different harmonics are the weights of these different copies of the Fermi-Dirac jump.
I see. So
This is coming from the Floquet wave function.
So you said two states of the same Floquet energy.
Which is this one, might have different Floquet waves. So imagine K1 and K2.
Yeah.
They could have the same Floquet energy, but they might have different Floquet wave functions because they are at different K.
Oh, I see. Okay, yeah.
And so the point is they will have different occupation in this steady state in general.
I see. Thanks.
We have a similar notion of kind of Leipzig theorem for this modified like Fermi surface.
That's a good question. I don't know. I also thought about this, but I don't have a good answer, I think. Yeah, so let's consider the case of a fermion coupled to a boson bath. So here, to be concrete, we imagine we have the same kind of tight binding model of blue sides that is being driven by an electric field. And now it's coupled to a collection of harmonic oscillators. So each of these bolts here represents a harmonic oscillator, and we're coupling just the density of the fermion on site to, let's say, the position of each harmonic oscillator with some coupling constant chi, okay? And these harmonic oscillators, they have a distribution of frequencies. So each of these bolts has a different frequency of oscillation, but we are imagining that all of the sides are kind of coupled to an identical collection of harmonic oscillators. So this kind of repeats. It's a completely periodic model, okay, in which each side is kind of coupled to its own bath, which is a collection of harmonic oscillators. So one can derive a kinetic equation, kind of Liouville equation with some collision operators. By the way, if you wanna, I recommend this book for learning all these kinetics of systems coupled to baths. So there's some explicit expression for these collision operators. So they are, it's a very kind of nasty expression and non-local in time. And basically it contains two terms. So one term that accounts for the transitions that the electrons do when they emit a quantum of energy into the bath, and another one that is the transition when they absorb quantum of energy from the bath. But starting from that kinetic equation that has memory and everything, we were able to show that in the limit of weak coupling to the bath, when this kind of coupling constant of the density of the electrons to the position of the harmonic oscillator, this chi goes to 0, in that limit, the density matrix approaches a kind of steady state with occupations. Again, here imagine just have a single Bloch band, and the Hamiltonian is just kind of driving that single Bloch band with a monochromatic electric field. Then the density matrix, the occupation of the states, then has this form with these occupations F given by the solution of a kind of Boltzmann equation, a usual Boltzmann equation. So transitions from one's initial state K to K prime times, Pauli blocking factor. So occupation of initial state times, kind of the whole occupation of the final state. The final state needs to be empty and the initial state needs to be occupied. And this all the information about the bath is encoded into these transition rates. They contain these emission and absorption terms. So, but these scattering rates then contain information about the Floquet wave functions of the density of states of the bath. So there's a kind of function there that knows about the temperature of the bath, the occupations of the modes of the bath, and density of states of the bath. So all of it is encoded into these functions. But the key point, or some of the properties of this Boltzmann equation is that it does not satisfy any more detailed balance. It only does it in equilibrium. So when you take these Floquet amplitudes to be such that only the L equals 0 term is non-zero, that's kind of the equivalent of going to a time-independent problem, then you can prove that this scattering rates satisfy detailed balance, but generically they don't satisfy detailed balance. And also they essentially behave like you have scattering in which energy is only conserved modulo omega. That's going to be kind of important, okay? So electron kind of transitions between different Floquet energies, states with different Floquet energies, and it emits a boson into the bath, and the boson only needs to satisfy that the energy is the final minus initial modulo the driving of the Floquet frequency, okay? And so these are just basically what we did is we just solved this numerically. Right? Solving this equation analytically is really hard. So as in the previous part, what we did is completely analytical. Here we just did numeric. So we solved this for the steady states of this Boltzmann equation, and we found a really unexpected kind of answer. The steady, so this is occupation of as a function of Floquet energy for a bath at 0 temperature in 1D, but also in 2D. The occupation, in general, is kind of very far from being close to Fermi-Dirac. The system has kind of reached a steady state with very broad distribution, but it retains some kink. As you see, there is some non-analyticity. In this case, it's a jump of the derivative. In this case, a jump of the second derivative. And as I will show you, it has to do with the fact that the density of states of the harmonic oscillators has to necessarily have a non-analyticity at 0 frequency, because you cannot have harmonic oscillator modes with negative energy. Those would be unstable. Just by the fact that bosons have to have positive energies, there is a non-analyticity there. That non-analyticity is what creates these kinks. And the most surprising thing we saw was that even when the bath is at finite temperature, the kinks remain there sharp. I think I'm a bit tight with time. So in a sense, the position of the kinks, as I said, depends on where is the non-analyticity of these modes of the bosons. The bosons always have to have a non-analyticity at 0 frequency because of this property that you cannot have boson modes with negative frequency. But if you artificially make a bath, for example, that has a jump of the boson frequencies at some finite frequency, the non-analyticity is here, then the kinks appear at different positions. So where the kinks appear is dictated by where does the boson bath have a non-analyticity in its density of states. So where do these non-analyticities appear? They have to do with the following, okay? So imagine first, for simplicity, zero temperature. So at zero temperature, the particle is only allowed to emit quanta into the bath because the bath is cold, it's at zero temperature, there are no phonons, or no quanta of energy to absorb from the bath. So at zero temperature, in equilibrium, the electron would just kind of jump down in energy by emitting quanta into the bath. And what establishes the Fermi-Dirac occupation from this kinetic point of view is just basically there's some kind of gravity pushing the electrons all to low energy by emission into the bath, and then Pauli principle. Once electron gets to some state, another one cannot go there, and so they all sort of there is a kind of gravity that tries to push the electrons to lower energy. Plus, Pauli exclusion is what gives you the Fermi-Dirac occupation from this kind of kinetic point of view. But now, because energy is not conserved, when the electron gets to the bottom of the band, it can scatter to finite K. Because even by emitting an arbitrarily low frequency quanta of energy into the bath. So this emission of very low frequency quanta of energy into the bath now becomes allowed between states that are distant, because energy is only conserved modulo omega. And that's where these kinks appear. The first kink appears when the bottom of the band is, at the K such that it's connected to the bottom of the band just by, emitting a quanta into the bath of nearly zero energy, but, doing one Floquet unclap. So the energy is just conserved modulo omega. That's where the kinks appear. But they remain sharp at finite temperature. You can compute, for example, density-density correlations. Because these kinks remain sharp, then the density correlations remain power law, even at finite temperature. So that's why we call it ultra critical. The power laws are different than the Fermi gas. So in a sense, that's why we call it a non-fermi-liquid. It has a kind of non-analyticity that gives rise to power law decaying correlations. It has, quantum oscillations also that remain sharp. They remain non-analytic even at finite temperature. The point in a sense is that this kink really does behave like a Fermi surface in observables. And just to maybe one last comment, something we're kind of playing right now, this is still unpublished, is that in a sense, the appearance of these kinks, the Fermi-Dirac statistics is not so crucial. So if we consider now a problem of bosons filling this Floquet band, you can model it with a similar kind of Boltzmann equation. The only difference here is that you will have a plus sign instead of this Pauli blocking factor that we had here with a minus sign for fermions, but essentially the same Boltzmann equation. But whether you have a plus sign or a minus sign here actually is not crucial for the appearance of these kinks. And so what we see is that the bosons also have these kinks. Even when they have a Bose-Einstein condensate, the steady state, the thermal part of the gas has a non-analytic occupation that has some kinks. So it's as if bosons could have kind of an emergent Floquet Fermi surface like a non-Fermi liquid coexisting with the Bose-Einstein condensate. Yeah, so I guess there are not many experimentalists, but just to mention again, going to very low frequencies, it's a very good idea experimentally, like microwaves. There, I think there is a real chance in very clean materials to reach true Floquet steady states, which I don't think they have been reached in other experimental efforts that have tried to reach some kind of Floquet occupation of bands. So there's still a lot of open, I think, potential for experiments in this microwave regime. Yeah, so just to summarize, when you take a system of free fermions, periodically driven, and they are coupled to a fermionic bath, with which they can exchange particles and energy, then the steady state is, instead of having a single jump, looks like a staircase with multiple jumps. But each of these jumps is kind of similar to a Fermi gas, okay? It's like a Fermi liquid. And the phenomenology is similar as if you had a Fermi liquid with multiple Floquet Fermi surfaces. But when the system is coupled to a boson bath, then you get a very non-trivial steady state with kinks. So it kind of resembles a non-Fermi liquid. And even more interestingly, these kinks remain sharp even when the bath is at non-zero temperature. So thank you.
So the sensitivity to the bath for experiments, is it a disadvantage or an advantage maybe?
Depends on how you want to see it, right? So in a sense, it means that you need to really understand what is the kinetics in each experiment. And it might be different, if you have a kind of gallium arsenide 2 deck is embedded, between two other huge semiconductors, right? Yeah, so you have to think more and understand what are the details of relaxations. But in a sense, it's also an opportunity because you have more room for getting different kind of states, right? Engineering and getting different kind of behavior.
And maybe the bath is the thing you're trying to probe in this context.
It's partly what you're trying to probe. So in a sense, one interesting question is, you see, in a sense, what happens is there is many possible occupations of Floquet bands, right? And the bath selects one of them in this weak coupling limit. So there is one that is special for this given bath. When you bring another bath, and it wants to select a different one. And so an interesting question that I'm kind of trying to think right now is, can there be a kind of principle that we could say, what makes this the right thing to select? It's like in equilibrium, we say, maximize entropy. So here, clearly, if you want to have a general principle, this principle has to be some kind of maximization or of something, but that something has to know about the bath. But maybe there is still some principle that is more general of why some steady states are selected over others.
So in the fermion versus boson bath, is there a distinction in the kind of conservation law? So in the fermion, the fermionic bath, it hops between the sites, and I trace some of the sites out.
Yeah.
So kind of the number of particles is sort of on the system that I care about is conserved.
It's not conserved,
It's conserved on average.
Exactly.
But on the bosonic bath.
Yeah, that's a good question. So in a sense, if I want to be more careful about this issue of different bath, I should also keep the same conservation laws. So you're right. But you see, maybe just to be a bit more nuanced, let's say, the point is also that even for bosons, it depends on, just keeping the same bosons, it depends on the density of states of the bath, for example, right? So here, if I take these two baths, I get the same occupation in equilibrium, right, for bosons. But now out of equilibrium, I get different occupations for bosons. And something I didn't say for fermions is that, oops, I went too far. This answer depends on the fact that I took this limit of the density of states of the boson of the fermion bath to be infinitely broad and flat. If I would take an actual non-trivial function of the density of states of the bath of fermions, this will be different. You will have still different jumps, but the strength of the jumps will know also about the density of states of the bath at that particular energy, for example. So yeah, that's a more precise way to make, because you want to compare systems with the same conservation laws. But even when you have the same conservation laws, this detail, for example, of the density of states, the precise shape of the function of the density of states of the bath will change the steady state. Yeah. Yep.
Just a naive question. I think you intimated that in the fermion case, when you take the frequency to 0, you can recover the usual Fermi-Dirac distribution, the driving frequency to 0.
So maybe it's more, taking the frequency to 0 is a very kind of complicated limit. So it's better to view it as keeping the frequency fixed, but just the amplitude of the oscillation, of the oscillating part to 0.
So I guess my question then is, let's say we do it that way, is there a similar limit you can take in the bosonic case to recover?
Yeah. So what happens with the bosons, I just don't have a good kind of plot because we're kind of here cranking up the parameters so that the non-analyticity is visible. But what is happening with the bosons really is, let me see if any of this looks better. I don't think, yeah, okay, maybe this one. With bosons, what happens is as soon as you have finite coupling, at any finite amplitude of the drive, the main jump, the jump that you had where the original Fermi surface existed, is smears, because the fermions acquire a kind of finite temperature state, the steady state. So the original Fermi surface kind of becomes this, okay, in the steady state. But somewhere here, it's just kind of hard to see there is a kink. And here I have kind of just crank up the parameter so much that the kink becomes visible. But the original jump is completely smeared. But somewhere here, there is actually a kink. It's completely invisible, at this level of the function. But when you apply a magnetic field, this is actually, magnetic field oscillations for this same one, and they have a different period than the one that you would expect from the original Fermi surface. The period of these oscillations is controlled by some kind of kink here that is not, it's not hard to see from the function itself. But the strength of the kink becomes weaker and weaker as you turn off the amplitude of the drive.
I guess you expect, yeah, maybe in the fermionic case that this thing survives interactions.
Yeah, so interactions, right? That's a very important and hard question. So what I expect roughly with interactions is the following. So when you have interactions, the steady state of the particles of the gas is hotter than what it would be if they were non-interactive, because they are colliding with each other, so they heat up more. So in the fermion case, that means that just because temperature smears out these extra jumps, similarly with the interactions, you will have just a hotter steady state. So this will be even more smeared by interactions. Okay. Now in the boson case, because the kinks are surviving at finite temperature, this effect will not destroy the existence of the kink, right? So the steady state will be even hotter, but the kink, never dies as a function of temperature. So that's kind of the, maybe let's say, simple answer to your question. I mean, there's a more complicated part that has to do with the fact that there is no the lifetime of quasi-particles in all this discussion of the system is always infinity because they are free, right? And interactions will also add a finite lifetime. It's possible that the lifetime, quasi-particle lifetime, will, likely smear the kink. But that's the hard question that we now hope to eventually tackle. It's much more complicated. But what is the true quasi-particle lifetime impact on this kink, for example?
So I get a feeling like the major difference between the bosons and fermions are they have different density of state. Like that's why you have the kink. That's my takeaway. So is that true? Like other details, for example, like the particle statistics doesn't matter, or does it matter actually keep the difference between different masses?
Yeah. So for the bosons, in a sense, at a very rough level, it does not matter, but in details it matters. So actually what we're seeing is that the kinks have different scaling in the BEC state and in the thermal state, when the Bose-Einstein condensate disappear. In the hot phase, the kinks of bosons have essentially the same scaling as in fermions. But the cold phase, the phase in which these kinks coexist with the Bose-Einstein condensate, are actually stronger for bosons than the fermions because they have to do with what happens with the scattering from the bottom of the band to this finite K state, and because bosons are occupy much more that state in the Bose-Einstein condensate, in a sense that helps and makes the kinks even stronger for bosons than for fermions. Yeah.
No further question, let's check the speaker again.